We're on.
Greetings, everyone. Welcome to our session today on Quantum Leap, the ever-changing virtual state of quantum computing. This is a new session that I think there's only been one other quantum computing area, but it's an area that we see as growing. It's coming fast, and especially with large language models, Gen AI, this seems to be the very next logical progression. My name's John Arrasjid. I work at VMware now. I'm a Boomerang. I work in the sales field right now.
I'm Tony Foster. I'm a technical marketing engineer at Dell and do all sorts of fun, crazy stuff, just in case you couldn't guess from the cape.
Cool. Now, this is a quick overview. We're not going to run through the details of the agenda, but just to give you an idea, especially for those who want to take a picture or who are watching it later on, this is what we're going to cover. We're going to get started on this. So, why quantum? There are a number of different areas that we've already identified use cases for. We're going to talk about that in a second. There's mining, navigation, secure communications, agriculture, edge, quantum imaging, and logistics. And as part of what we're seeing on the AI space with customers, we see the same thing on the other areas. So we've got an example that
One of my favorite examples on this is actually the agriculture one. So the population of the world is growing. We've got to be able to feed them. And with quantum computing, we can actually figure out how to optimize some of our growth patterns and stuff with food production to actually be able to continue to support the world's population.
Great. So what is quantum physics? So we're going to cover two things. I'm not going to read through all the details, but the key is quantum is a share or a portion. That's the definition. Quantum theory is around the theory of matter and energy. So there is a connection with compute, and you'll see in a moment. Quantum mechanics is actually applying the quantum theory and the approach in going forward with that.
So what we have with quantum computing is real interesting because you actually start with a single atom that's spinning really fast, and we have to slow it down. So we supercool it, and right now the most common way to do that is as a single solitary system, and we have that here. And we'll take those solitary systems that you can see in the little diagram, and we'll keep building those out, and we'll put a collection of those individual systems into, go ahead and click, a much larger system so that we actually get a quantum computer. And it's super cool. It's got what's called a chandelier that holds all of the different qubits in place so that the processing can happen. And then you have a actual Google quantum computer here where you can see the chandelier and the QPU at the bottom of the system. And with those qubits, basically what we get is an awesome little spinning atom that's near absolute zero, so we've slowed it down so we can look at the state of it, and it's sort of like a coin flip. We don't know where that coin flip is, so when the coin is spinning in the air, it's in an unknown state. It's sort of like Schrodinger's cat from the previous slide. We don't know until we open the box what the state of the cat is.
Now let's talk a little bit more on the terms and concepts. So in this area of quantum computing, as well as in quantum physics, there's this concept called superposition, where there are quantum particles that can be in all these different states, as just described. That's the Schrodinger cat or the coin flip comparison. There's entanglement. This is where you have quantum particles that interact with each other, and they can influence each other for different final outcomes. And then finally, there's a quantum quantum interference, where that interaction can be both good and potentially bad. It all depends on how we use this and how we're looking at what's called the probability outcome. So for example, when we look at how this process works on the next slide, we basically have the ability to actually look at all these different combinations of ways of doing things. There's a probability. The highest probability is the answer that gets conveyed. And that's something similar to what happens with Gen AI and large language models as well. Let's see, go to the next one. Yeah, I'll let you go ahead.
Okay, so really if you think about it, let's start with the classical model. The classical compute model, everything's done in ones and zeros. Everything comes in binary, and you have inputs and outputs. Go ahead and click again for me.
Yep.
And with quantum computing, it doesn't quite work that way. We have inputs that we feed into our quantum computing. They go through a bunch of gates and everything to try and take care of the noise and everything that John just discussed. And what comes out on the other side, the outputs, is going to be the highest probability item of what was calculated. So it's not going to be 2 plus 2. It's going to be what's the highest probability that the coin is a heads up.
Yep. So I want to talk about the use case in financial, or the set of use cases in financial. There's risk profiling, there's trading optimization, there's targeting and prediction, there's security. And I will tell you right now, as you can see, the definitions of these areas and the use cases, we use ChatGPT for this as an experiment because our ability to do this has some similarities to what you do in the OpenAI space. So this gives you, I'll let you read this later on just for time's sake, but we did validate all the info we got back from ChatGPT and agree with what we have on these definitions here. So who's in this space? We have a number of different companies that are working on the actual physical hardware. We have some that are working on simulators so they can start preparing and developing the hardware aspects. We also have companies like NVIDIA that have their DG platform series that is being used, although it's GPU-based, it's not quantum-based. But it's an area to start moving the bar forward with research. And again, all of these companies are working towards having simulators so that they can start learning more while the hardware technology is getting developed.
Absolutely. And you'll see with a lot of these, a lot of them are building physical quantum computers. You still have to figure out how to program them, and that's where the simulators come in. They're not running full things through there. They're simulating the likelihood that something will happen while they still get their hardware developed.
So this is from IBM from about, I think it was about 2 years ago. And this is kind of their prediction on how the path is going. I've heard similar results from Intel and others based on the research we've done. They're looking at maybe just like what we've seen with development of GPUs in working with cloud and multi-cloud and obviously virtualization. The same thing they see as applying, and it's expected that it's within the next 10 years that we'll see full evolution in this area. But the thing is, there's a starting point now. I do encourage those of you who are pursuing ongoing development in cloud and working with AI and potentially some of these other verticals and the use cases that we mentioned, this is something you should start getting to be more familiar with.
So this actually starts getting us into the meat of this, probably why many of you are here. When are we going to see quantum computers in our data centers? And the answer is probably not super soon. It's probably going to be a little bit before we actually see them in our data centers. And if you think back to the first computer, the ENAC that we have here on the screen, it had hundreds of miles of cables and took tons of people to operate. And if you look at a modern supercomputer, it has hundreds of miles of cable, liquid cooling, and takes tons of people to operate. So there are very, very similar instances there between the two. So we're still in that developmental phase where quantum computers are starting to become available, but they are not readily available and probably won't be for 10 years. After 10 years, we will probably see them. Now, let's apply this to virtualization. This is a virtualization conference after all. So how do we see those being consumed? Obviously, they're going to be the most expensive processors out there. So you're going to put that towards the most expensive thing you can. GPUs are a little bit more expensive than standard processors. So it's just going to follow that curve right on up. Your most expensive thing gets it. And what we see is those most expensive items in terms of risk, in terms of rewards, are things that require high-speed operations, such as stock market and trading events, and security events. They contain the most risk. Now, the way that's going to probably be consumed in a virtual environment is through a cloud. You're probably going to have some sort of cloud provider who's going to deliver quantum computing for you so that you can actually get the benefits of quantum in your environment as opposed to having a super cooled environment in your data center.
And we're seeing something like this with, obviously GPUs and current AI. NVIDIA's doing this, offering cloud. You can see on the VMware stack, we're supporting virtualization of GPU and working with different service providers to make that more available. We expect the same thing is going to happen in this area. We don't expect companies to buy quantum computers to run on-prem because of the cost. They're going to take advantage of this partnership with different cloud providers and the vendors. And our last slide, I'll let you go.
Awesome. So obviously with stuff virtualized, with containers, with all the wonderful stuff that we are developing now, what could you do with a quantum computer if you start putting it in a large language model? You could do some very, very interesting things. It could become very interesting adding it as a hidden layer inside of a large language model. You could get very close to a sentient system at that point if you really thought about how many qubits you put in there and what they were able to do. So the possibilities really start becoming interesting the further out we go with this. And go ahead.
So I was going to say, in summary, this again is what we've tried to cover today. If you have questions afterwards, you can reach out to us. Also, I wanted to share that we have a number of references on there you'll be able to get once this recording is up, which I think is probably going to be later today. And we also wanted to give you our contact info if you want to have follow-up or questions or anything. We'll stick around for a little bit after this, and we'll probably go outside of interference area, so we'll be over on the left side. So thank you so much for joining us today. Well, thank you.